Welcome to Green Giants, Titans of Renewable Energy, a podcast where insights and innovation meet. Every episode, we dive into conversations with industry leaders, experts, and change makers, bringing you the stories and ideas in the renewable energy sector that shape our world. And now, let's jump into today's episode with your host, Wes Ashworth. Welcome back to Green Giants, Titans of Renewable Energy. Our guest today is Tony Roulstone. Tony has spent his career inside some of the most complex engineering environments in the world. He has worked across UK Atomic Energy Authority, Rolls-Royce's nuclear and aerospace businesses, major engineering program recovery, corporate transformation, consulting, and nuclear education at the University of Cambridge. And before we begin, you don't need a background in nuclear engineering to follow this conversation. We're going to explore three things. First, why brilliant technology can still fail when the organization and delivery system around it break down. Second, whether small modular reactors can make nuclear more affordable by turning nuclear from a one-off construction project into a repeatable industrial product. And third, what would need to change in financing, manufacturing, workforce, safety, and public trust for nuclear to scale. At the center of all three is one question. Can nuclear become an industry that repeats success instead of rebuilding the entire system for every new project? With that, Tony, welcome to the show.
Thank you very much.
It's a pleasure to have you. And this is a very hot topic currently. And your career does give us that sort of rare view across engineering, aerospace, nuclear energy, and business transformation. And I want to begin with what those environments taught you about the difference between invention and execution. And so what separates a clever technology from one people can really depend on?
Well, it is an exciting time in nuclear. We thought we had identified a nuclear renaissance 15 years ago, and it wasn't there. But there is one, there's a lot going on now. So it's great to be able to talk about these things, both from a perspective of what's happening in the US and what's happening in Europe. I spent a dozen years in the army. In a very practical world, I was trained to fix helicopters, and they sent me to a tank regiment. And it was about fixing stuff, very hands-on. And when I came out of the army, I joined the Atomic Energy Authority and then Rolls-Royce, and I learned that actually engineering is very much more about theory and modeling and then practice and testing. And the thing that I think you were asking about is one can have all sorts of bright ideas. There's lots of bright ideas around at the moment. What distinguishes a bright idea for something that's going to last and work? And I think it is this combination of modeling and testing. It really at the heart of what Rolls-Royce does is its engineering. It has very good engineers who get in the computers and model stuff, but they always go out there and test beds and destroy engines and look at them and look at the effect of it. And it's a combination of these two things which makes something that's reliable and can be dependable. And then you can then franchise it out and get lots of people to do it. And these two things need to go hand in hand.
Yeah, and we'll dig into those two things a little bit more as we go. But it's that idea, like proving something can work is very different from proving that people can really depend on it every day and kind of go into that execution. And you brought up Rolls-Royce. I want to talk about an example, not necessarily nuclear, but that I think connect and we'll tie it in here. But at Rolls-Royce, a failure to deliver the FedEx control system left engines unavailable and Boeing 747s sitting in Seattle. Tell us a little bit about what had gone wrong and what did you discover once you got inside the problem?
So that was very interesting for me. I'd been running the electrical control unit in the nuclear business, and we'd struggled with some of the same issues that they were struggling with, which was that nuclear is a sort of mechanical engineering physics area. Aerospace is full of physicists and mechanical engineers, but actually microprocessor and control systems and software are bringing wholly new challenges. And what we found when we went across to aerospace was we couldn't make the black boxes which control these modern engines. Therefore, we couldn't deliver the engines. And because we couldn't deliver the engines, there were 747s, there were 747-400s in those days, sitting on the tarmac in Seattle with concrete blocks instead of engines, destined for BA and Qantas. And BA and Qantas were not at all amused by this thing, and Boeing were livid about it, and they wanted something done. You can focus on the black box, but the real issue was that the organization had grown up with a lot of people who were mechanical engineers into governors and gearboxes and oil systems and such like. Actually, this thing had come out of left field. Instead of electric's been about contacts and sparks, and it was then about microprocessors and software and complexity. And the FADEC system, the full authority digital engine control on the 747, which is now absolutely routine, but then was brand spanking new. is the biggest electronic system on a 747 other than the flight control. So here was us and Rolls-Royce in Derby designing the biggest outside the flight control system for Boeing and feeding into this thing. And there were growing pains and struggles. And we're working with a specialist supplier in Birmingham. And between the two organizations, we won't make a very good shot of it. So what we needed to do was some immediate actions on trying to fix the problems that were there and then try to find much more productive ways of forward. And I think partly my experience of coming from nuclear, where we'd done more of this systems engineering, but also looking at the organization with several hundred engineers. And in there were some very good systems engineers, but they were quite low down in the organization. The organization wasn't focused around with systems. So when one or two people decided to move on, we reorganized the whole thing to bring systems really to the surface and give them an overview and bring the systems practices and the people who knew about it, knew about software and systems. We brought them up the chain and we retained all the old skills, but this enabled the organization to run much better and to face the challenges that Boeing set us and then Airbus set us. And I remember having to go and tap the boards at Boeing and at Airbus to explain that we were going to do what they wanted us to do and it was going to work out, but you had to give us a little bit of space and time.
Yeah, it's a great example and just that journey and kind of learning through that. And I'll tie this back to nuclear just to make that direct connection. So what did that experience teach you that still applies to nuclear projects today?
There's a lot of know-how in the industry, but the industry moves along and the focus of these things moves. So if you go back to the old days of nuclear, it was ruled by physicists. That was the really sexy bit about nuclear, and everybody who's at the top was a physicist. That's not necessarily the case now. I mean, software and systems is very important, and hydraulics is important. Materials is an absolutely crucial thing, which the physicists might not understand. And so it's understanding that you need the range of technologies and you need to listen to them all, and you need to move with where the focus of the industry. We'll get on to economics and business experience in due course, but the nuclear industry has been dominated by very bright, very capable mathematicians, physicists, and theoretical engineers. And probably they're not the most important thing that we require, at least with the existing technologies now. We need people who can craft these and work with supply chains and get things done in a completely different manner to be effective. And I think probably we're going to talk about that.
Absolutely. Yeah, I think, looking at this sort of aerospace example gives us this useful lens for nuclear. And, the reactor may be technically sound, but as you're saying, like the system responsible for delivering it, that could remain, fragmented, temporary, and inefficient. And so that maybe is even more valuable. So, and I know you've made this comparison to sort of large nuclear construction to say like building a 747 in a plowed field. Tell us about that. Like, why is this such an inefficient way to build in terms of how it's been done?
I only spent quite a short time in aerospace, but this sort of aerospace ideas, analogies, I often go back to. Perhaps the experience there was important. It was actually brought to me when I went to a nuclear conference when someone said, well, we've done some analysis of the Westinghouse fall at PWR and with AGRs and actually they got the same amount of connections and valves and pieces and didn't have rivets, they're welds. As a 747, this thing on the ground is just as complicated. It doesn't have to fly, but it has to make power. It's just as complicated as a 747. And I said, well, how do they make 747s? Well, or anything else, 777s nowadays? Well, they have a sort of production line in Seattle, the same at Airbus. And they move them along one month at a time and people do all the work. It's systematized and they got the systems on the paperwork and they got the material flowing to the station they're going to do it. It's not quite like a car factory where they just move, along its 2 miles an hour and the cars goes through in 6 hours. It takes several months, but the same idea of systematization, getting the tools and equipment, coming to the people, and coming to the work is important. When you look on a nuclear power station, I'll just give some facts about we're building 2 very big reactors in the West Country at a place called Hinkley Point in the UK. They are some of the biggest reactors in the world. But currently there are 13,000 people on site. They started building in 2019. And when you look at a picture of it or you see a video of it, you see these forests of tower cranes and you see the concrete being poured and you see that the caves that people are trying to build around the reactor and then they're going to fit piping into it, and then they put instrumentation and wiring into it, and it all has to be separated. The complexity of building these things makes it pretty odd that we're doing such a complex quality paper-bound inspected system in a field, which it is. It was a field before. We've dug a hole in the ground, put some concrete down. It's a field. The people who've been doing it have been brought from all sorts of subcontractors because they take so long, these things. It's not as if you've done one last year and we're going to do the same job this year. You've probably not done one. We haven't built a reactor in the UK for 30 years. It's the first time. It's the first time for people. That's not how to build complex systems, but it's probably the only way you can build these very big reactors such as EPR in Europe or AP1000 in the States. So it's not surprising that these things take a long time. The site is very unproductive because you can't get access. People have to almost crawl over each other or get clearance to access the site. They have to get the right material and paperwork and inspectors to go to every place. And then they need it signing off and then some other inspector to have a look at it before the next guy can get into it. It is just the wrong way of building something complicated. So I use the analogy of building a 747 in a field.
Yeah, it's such a powerful image that immediately kind of clicks when you think about it. Just nobody would deliberately choose to manufacture aircraft that way. And
it sounds like I'm moaning about the people who do it. The people who make these things do almost superhuman things. They make things and they do not stop until it's high quality. They do not stop until all the paperwork's right. And they don't stop. It just takes a long time. And you find that organizations who have done it before recently are much better at it. So in the 1980s, the French built 33 Westinghouse PWRs and 24 4-loop Westinghouse PWRs, very similar but slightly bigger. The crews built them in 4 or 5 years, and they built 2 on a site, and another 2 on a site, or they moved between sites. And so they built up a know-how about how to do this extremely difficult task and manage the paperwork and the flow of materials because in their bodies, they learned the practice of doing this stuff. And so you need extremely experienced and skilled people to do this thing, and you need a program. So instead of a production line at Boeing, we had a production line of them, and they moved the people being between sites, but then they were doing the same sort of thing on the same sort of reactor down the road, and they got very good at it. And of course, more recently, the people who got very good at it are Koreans. They took a American design, called CE Combustion Engineering System 80, and they adapted it, and they've called it OPG 1000. And they built one of these a year, generally on very similar sites. So you can see sites in Korea with 4 or 6 reactors on the site, very similar designs, and the people who built them. And this is now not the nuclear physicists, this is the welders. It's the guys bending the reinforcing rod and putting the concrete down. It's the planners, the detailed planners. It's the schedulers. It's the getting the materials. It's the guys who do the inspection and the guys who keep the paperwork tidy. All those things work. And I know I visited China 10 years ago and talked to people at CNNC and CGN, the big builders over there. And it was very funny. We worked on our project there, and they worked on the other people's project, and then they worked on our project. So they were all working on each other's projects. And I thought this very odd, but actually it was really important because they realized the skill, although these designs were not a big difference, but there was a difference between the ones built in the north, which were Chinese design, and the ones in the south, which were French design. But the practice of working on site and getting these things done to a high standard and getting the paperwork organized, they'd learned the best way is take the guy who's done it before and get him to do it again. And then we'll move him to and get him to do it again, which under their centralized control, they can move people around. But this business about repeatability, if you're going to have to build these complex devices on sites, is really important.
Yeah, I appreciate you pointing that out as well, too. I think some of the sort of lost knowledge and experience and some of the things that are happening there with that sort of shared execution, it just creates a different kind of knowledge and that combination of ideas. And I think those hardest skills often live in teams, routines, judgment, and experience rather than in manuals. So important to get that right. And so I think we've now successfully sort of painted the picture of current state, some of the opportunities and how it's been done before, and now kind of moving into some of the new ideas, which I'm sure people have heard, but I want to dig a bit more into, which is really first into like SMRs, which are hyper buzzword right now and a lot of stuff going out there. But, their SMRs are presented as a way out of the one-off mega project model. And the real promise is not simply a smaller reactor. It's a different production, financing, and delivery system, which we started to kind of get into there. But SMRs are presented as the answer to maybe that broken model. Why is a smaller reactor not necessarily automatically a cheaper reactor? Let's start there, and then we'll dig a little bit further into it.
Okay, so we started looking at SMRs about a dozen years ago. And at the time, when we talked to people, they just said, you're mad. And they said, you're mad because everybody in the nuclear industry believed in this immutable law of the lower costs of larger scale, the scaling law. And they'd enacted this throughout the nuclear industry. If you look at American designs, 1970s, there were 300 or 400 megawatt size. Well, this idea, interesting, came from coal power, where it definitely did work. It worked in the Europe and in the US, where they built smaller coal plants, bigger ones, and they got economies of scale that the cost didn't go linearly with the size of the output. For nuclear, they absolutely believed in it, and every time they had a cost problem, they just designed a bigger reactor. So it was 300, 400 in the early 70s. It was 600 to 800 by about end of 1970s, then 900 in the early 1980s, and then 1200 somewhat later in the night. And nowadays, there are designs which are, the EPR is 1700 megawatts. And if you talk to any designer in one of these big design houses, they say, absolutely, anything small is going to cost more. And we have made them larger in order to get the economies of scale. And if we haven't yielded them, we can't see the benefits. It's because of other effects. And this is the problem. So there's some neat way of calculating this thing. But one of the problems is when I looked up, some statisticians had done some work in the US, actually, then elsewhere. And they said, when we look at the economies of scale in the cost of the 100 reactors we built in the States, we can't find it. We just can't find it. It doesn't seem to be there. The smartest thing that was said was, by what some of these statisticians, was there may be economies of scale, but larger reactors take longer to build. So instead of taking 6 years to build, it takes 8 years to build. And because you have this standing army of administrators and overheads, any cost savings get consumed by the longer duration. And therefore, there may be cost savings associated with making them larger, but they take longer to build. And so the bill at the end is no less. So this has always been saying that if you reverse this argument for small reactors, you say, well, it's going to cost more. You build them just the same, they're going to cost more. And they will also say that you sort of need the same minimum number of people to operate a reactor. In fact, I think it's actually legally required in the US at the moment. There's so many operators and so many security staff and so many health physics people, whether it's right or wrong, but per reactor. And therefore, it's going to cost you an operating cost. But if we just stick to the capital cost, which is the biggest element in nuclear, how do you square the circle? How do you get the benefits? The idea that we've been doing research in and is by using a smaller size of reactor, we can take work away from sites because the bits you're doing are smaller, and you can put it into a place where you can have a higher productivity. You've got better tools. You can have the systems that do all the documentation and bring the inspectors at the right time in place. And also you can have the flow of goods and tools towards the people, not the people having to go and find the goods and tools. Therefore, factory manufacture of as much as you can is really important. But you have to design it. It has to be designed at outset for what we call design for modular manufacture and site assembly. The work we did basically says that if you build a small reactor the traditional way, using on-site with concrete and rebar and wiring coming there, actually they will cost more than a large reactor. So anybody who wants to build a small reactor in a traditional way has got a big hill to climb. Only if you think about the strategies. There were 3 strategies that we identified. One is a radical idea of standardization. Again, the nuclear industry doesn't really standardize things. They like to tinker and change the design. They either change the design, or they change the prime contractor who does his own detailed design about how he's going to build it, or he picks his own turbine, or he picks his own pumps, or he picks his own supply chain. And so, unfortunately, the best example of this is in the US, where there's 101 reactors built in the 1970s and 80s. And apart from a couple at Diablo Clanin, they're pretty well all different, even ones on the same site, even provided by the same reactor vendor that built at a different time. They're not the same. And so this idea of radical standardization, which is absolutely routine in other high-tech businesses, you don't customize every one to every customer or every site. It's too expensive, and it doesn't lead to reliability and such like. Standardization. And standardization is also important for the other two steps. So if you don't do standardization, you can affect step 2 and 3. Step 2 is modularization. Taking the design and make it into chunks and making those chunks so you make in factories. A reasonable amount of stuff made in factories at the moment, the vessels and the turbines and the control system and the fuel and such like. But this is only probably 25% of the cost of the unit. So you've got to really dig in and say, what else can we do? How can we modularize? And certain things are quite easy to modularize. There's things like some of the water treatment and water conditioning systems. You put all the bits together on a little frame, make it in a factory and put to site. You just have to connect it up, nice and easy. There are more complicated things to do with a lot of the steel work, which you could make into sections and you can take it to site and weld it up on site and bolt it or do something. And then there's more complicated things, because the thing that's really time consuming is all this concrete and rebar. Concrete and rebar in nuclear, unfortunately, is very complicated and also has high quality standards, because people want to be able to demonstrate they can work after an earthquake. And therefore, instead of rebar being the reinforcing bars being half an inch in size, they're 2 inch in size. And instead of them being spaced 4 inches apart, they're spaced 3 inches apart with an inch between. You've got to pour concrete in between these things. And by the way, they also have to be tolerant, so they can only be a little bit out of whack in terms of space. The story, which I thought was apocryphal, but I've had it confirmed so many times I don't think it is. At Hinkley Point, because the safety inspectors inspected the rebar, big cages where they had the foundations, they said there were 70,000 anomalies where the rebar wasn't spaced correctly. So each one of these things, that they had to do computer analysis, which cost several £1,000s of each one, each condition. And if you multiply that out, it's about half a billion pounds. And the irony of this thing is, when you reanalyze these things for the tolerances, they didn't find any have failed. So actually, it was a design fault that said, well, you're going to have these spaced like this. But there was a tolerance which was acceptable. If they'd done that, save $500 million. Wow. Anyhow, that's the second stage. The third stage is when you have stuff in a controlled environment, something that appears in every other industry is production learning. So this is embodied know-how, learning on better practices as you go along. If you have people who do things quite often, once a month or once every couple of months, they say, well, we did this like before, we can do exactly the same, but actually we got this stuff in first, it'll take us a shorter time, or we get that paperwork, we've got this chap to appear, we can do it in less time. And it's a well-proven thing. Every other industry does it. When you look at the data for nuclear industries, absolutely no evidence of learning. And it's probably not because there's no learning. It's because the time between these events is so long that people forget, as well as this learning idea, there's a forgetting idea. If you don't do things for a couple of months, the guy moves off, or he goes sick, or he concentrates on something else, or he's promoted, or he goes on a training course. And so there's collective forgetting. And if you have a year between things, any learning is lost, is forgotten. And so you do need a flow of this work, which is similar, and same people doing it to get learning. But these three ideas, standardization, breaking to bits and modularization, and production learning, which means you have to have a series of these things going forward. That's just not possible with these very large reactors. Large reactors cost $10 or $15 billion a unit. It takes a lot of effort and people putting together to find that money to build a couple. The couple have been built, Mission Vogel in Georgia. That project's been going on for 20 years. It's a big affair. But if you have smaller reactors, which you say a couple of billion, you can raise that sort of money as long as you're confident you're going to deliver it on time, it's going to work. But if instead of taking 10 years, it takes, say, 3 or 4 years to build, the financiers like this, so you can then, instead of building one big reactor, you can build half a dozen small reactors, and you can get this standardization, production learning effect, and you can make it more product-like. I'm not saying that you push the whole reactor out of a factory, but you can make it more product-like, and this is what the object is.
Yeah, it's such a useful explanation, and you've made such a great case for SMRs and sort of like why it works. And I think that the counter arguments too, where people might go to, the upfront cost of the capital expense initially, and then why that really makes sense when you look at the long-term sort of holistic view of what that will mean when it rolls out. So it makes a lot of sense of why SMRs are getting so much attention and why this is starting to happen.
So I use SMRs to mean light water-based. So all the reactors in the world, apart from the ones in the UK, are based on light water, water or pressurized water reactors. We know how they work. 18,000 reactor years of operation in the West and China and Japan, which is all very good. And another 18,000 in submarines that happens. So we know how light water reactor works. So the innovation in this space is not in the reactor technology. There might be some fiddling, but fundamentally it's about how you change the production approach for this. And the success of this is about not the reactor physics, not the thermal hydraulics. This is about quality and investment and factories and organization, such like. So these skills of business management and more in the engineering space are very important. I just wanted to talk about why I'm sort of optimistic about this possible happening. There are three or four, well, half a dozen designs going around, but there's three or four which have attracted quite a lot of orders and projects. And this is absolutely key. You can't build something of this scale and complexity unless you've got, and the infrastructure that goes with this and train people, unless you've got an order book. Again, Rolls-Royce, we didn't launch an engine unless we had an orders for 500. How are you going to pay for the development costs? And how are you going to pay for all the setup and such like? And nuclear things tend to be built one-off is pointless. So you've got to have a decent order book. And GE have got an order for 4 in Canada they're building. There's probably others going to be built in Saskatchewan and TVA. They've got orders in Poland and I think Slovakia, and there'll probably be others. So I think they will get to very close to the minimum order level to build a proper supply chain and organize to this. And Rolls are in a similar position. They've got order for 3 in the UK from the UK government, but they'll probably be 6 or 12. They've got orders for 6 in the Czech Republic, 3 in Sweden, and there's opportunities in other countries in Holland and elsewhere. And so this minimum order level, which is absolutely fundamental and completely unknown in nuclear, to have this sort of thing to work at, is possible. And there are other people out there, Holtec are a little bit behind, but they may well get to the same position. They've got some orders to do with data centers, and NuScale, who were leading, now getting some traction with some of the big companies, Entra, want to build, I don't know, some of these things down in TVA. Other people in the States are saying, well, these are the reactors out there. These are the things we're going to build, so let's build a lot of them. And this will enable them to start facing the industrial problems rather than the technical problems.
Yeah, absolutely. Great context there. I appreciate you sharing that as well and getting into that. Before we move from SMRs, any other kind of key things you would want to share the audience should know?
The World Nuclear Association does a tracker of how many SMR projects there are around. This includes light water-based ones and also these ones we're going to move on about with novel coolants, gas, molten salt, and liquid metals, so-called advanced reactors. And they say there was, when I last looked, 127 small reactor projects that have been done seriously around the world. They're in every continent, major countries. There's lots in the US, there's lots in Western Europe, they're in China, they're in Japan and Korea, there's some in the Middle East. The only people who haven't got any are Australia, because they've got a moratorium on nuclear in Australia, but they're fighting that at the moment. So there's a lot going on, and it's going on across the board. And this is why I say there's the nuclear renaissance going on, because not all these 127 will succeed, but there's so many of them, and a lot of them are funded privately. The old style was you wait for the government to give you money, and if the government to give you money, don't do sit on your hands till they give you some money. And then the vendors used to spend money, but most of the vendors, because there's been such poor industry revenues for the last few years, they just haven't got balance sheets to do anything. The new factor is private equity are coming in and saying, well, you can have $1 billion for this, or you can have 10 billion for that, or 5 billion for this, or we'll give you this and we'll give you this later. I mean, there's a good example. Just recently, there's a small company called Valar making a micro reactor, and they've just gone and done an IPO and raised $1 billion. And this is a company of, I can't remember, 50 guys down somewhere in, and they've got a design. They went through the first stage of President Trump's criticality exercise and used this to leverage to raise real money to build some reactors.
I think great context and helps us really understand like what is really happening in the world of SMRs and other reactors as well too. And as a part of that, I know we started to touch on, but just a lot of talk about SMRs. Also, coming up more now, like advanced reactors. You're starting to hear more about that, and some promises of more radical changes, in fuels and coolants and pressure, temperature, safety. It creates opportunity. Also creates another maybe layer of execution risk. But with advanced reactors, again, promising something more radical. From your perspective, like which advanced reactor idea has the strongest maybe practical case?
It's also will be contentious, but I'll give you some sort of general figures. These things are best characterized by their different types of coolants. So you've got high temperature gas cooled reactors. Gas might be carbon dioxide or helium. And we know a lot about that in the UK because we had advanced gas. We still have advanced gas cooled reactors. But these go to higher temperatures. And they actually go back to the 1960s when the first Dragon reactor in the UK, and then there were other ones in Germany and then in South Africa. These high-temperature gas-cooled reactors, much studied in the States, but not built in the States until recently. What they offer is more efficiency because of these higher temperatures. And they haven't, either because the experience in the prototypes have been going around, or the ADRs in the UK. We've got a lot of operating experience. And one of their key things is they use this new fuel, triso fuel, which is a ceramic fuel. Instead of putting a ceramic fuel in a metal tube, which is the usual approach in reactors, they put it in a coating of silicon carbide and high-density graphite and more silicon carbide and such like. These 1 millimeter fuel pellet pimples surrounded by these surrounding layers retain the fission products. Because now all ceramic, it's almost impossible to melt. Instead of metals which melt 600, 700, 800 centigrade, we're talking about 3000 centigrade to melt these ceramics. And so this makes them inherently very safe. And when you add this to the fact that they have rather low power density, that you can have what might be called an incident, and that is you have a power change, but you don't do anything about it. The actual reactor shuts itself down. It's very tolerant to operating outside the normal envelope. And the Chinese who built the reactors called HTRPM, they've demonstrated this just recently. It's interesting. They're using actually Western technology, which was put into a project in South Africa called Pebble Bed, and that ran out of money. And then the Chinese bought this Pebble Bed technology from them. Anyhow, they built the reactor and they've shared all the information. They show it works. And this technology now has been taken up by X-Energy, who have projects in Texas with Dow to build some smallish ones, about 100 megawatt electrical, slightly less, and a number of these things. And Dow want both power out of them, and because they have very high temperatures, perhaps 700 or 800 centigrade, they want to use some of the process heat for some of their petrochemicals. So that's the first type of advanced reactor. And then changing coolants, you can use, maybe something odd to people, you can use liquid metals. The traditional one to be used has been sodium or sodium-potassium mix. Sodium melts at about 75 centigrade, and it's liquid above that until it boils at about 800 or 900 centigrade. So you've got a very big range in which it's a liquid, and it's got very high conductivity, high thermal capacity. It takes a lot of energy, where you can have very dense core, and their advantage is because you don't slow the neutrons down, you can breed new fuel from old fuel. Using these fast reactors, you can breed fissile fuel using these high energy neutrons, and they were popular and they were researched around the world for this feature of breeding more fuel. And the third, and there's various people in the US, Oklo are very noisy proponents of this. Bill Gates has funded a project called Natrium using EBR technology and a bit of Prism reactor from GE. And he's building that's further ahead. It's got a ticket from the NRC. They're actually building and doing real work at Kemmerer in Wisconsin. That's a real project, whereas Oklo is a bit further behind. And there are other people in Europe. Just mention that other people say rather than have sodium as a liquid metal, there are other ideas of liquid lead. And this has been pursued in Sweden and in France. The third type is the most novel. There is quite a lot of experience because of all these countries in liquid metal. But I have to say this because there's very little experience in the next one, but a lot of enthusiasm around molten salts. So you take something like table salt, and it does melt at about 350 centigrade. And once it's molten, it conducts heat. operates pretty like water. It's not very viscous. It flows around. It takes heat away. It's quite good. Most people don't use salt, which is sodium chloride. They use sodium fluoride, partly because it's got better physics characteristics. You may mix it with other things, lithium and beryllium, but the same idea. They freeze about 300 centigrade and they're liquid up to very high temperatures. And they operate in a sort of similar way to molten liquid metal ones, but they don't have the problem for liquid metal. Sodium, if you've done experiments at school, you mix them in air, they burst into flames, and you add water, they produce hydrogen, it's burst into flames. So the sodium-cooled fast reactors have this thing you have to protect against, where the molten salt ones don't. It's a very open space. So there are people who have fast systems, that's with high energy neutrons, people who have moderated neutrons, you have people who have chloride salts, you have fluoride salts, you have with beryllium or without beryllium, and you have ones which have fuel dissolved in the salt, and the other ones have fuel in tubes or in triso particles. So actually we don't know what the right answer with molten salt is, but everybody is trying everything, I think is the answer.
Yeah, absolutely. A good overview of just the different technologies that are happening, some of the advancements and things like that. And you brought up a couple of them kind of tie back to safety. And I do want to bring this up. I think obviously new technology may improve the safety case, but public confidence is still shaped by nuclear's history. So what's the clearest answer you can give to someone who associates every reactor with a Chernobyl, a meltdown type of event? How do you clear that up?
So I teach at the University of Cambridge, and one of the things we make sure all students do is they do a course in nuclear safety, and part of we go through all the terrible accidents, and we do it early on, and they're all very glum about it. But I think it's instructive to learn to face the issues and to learn from them. In the case of Chernobyl, which is the one that's got the most profile, there aren't that many actually, so it doesn't take long to go through, but they are very instructive, each one. Chernobyl, everybody probably seen the film as such like a terrible thing. There are two really significant matters there. One is the reactor wasn't stable under all conditions. What I mean is, if you have the reactor operating and it's somehow disturbed, it should go back to its previous state. Very odd characteristics that in certain configurations, when he did the obvious thing, like push the control rods in to produce the energy, it's actually the energy went up, not by the way. It was a known problem by the Russians. They did know this occurred, and they tried to have rules to avoid it. But this led to the second issue, which was the way that safety was managed and the organization and management of it was not very broad and very questionable. So at the time of Chernobyl, they were doing an experiment to do with getting energy of a rundown reactor to keep running the feed pumps, to keep providing power, even though it's going to be switched off. And so the people came to do this experiment. There were people who were operators here, and they didn't seem to know what they were doing here. And between the two of them, they blew the reactor up because this lot disturbed it. And these people, it was actually in a very odd configuration towards the end of its life and of its fuel life, with all the rods drawn out, probably beyond the limits of what was allowed. So they should have never been drawn out there. There were rules against this, and they had this disturbance, and the reaction, they put them in and the reactivity went up, and the whole thing went up. So there was a fundamental design fault of not having a stable reactor. You want something stable in all characteristics. Again, getting back to aircraft, you want to be stable all the time. If there's a perturbance, it goes back to normal. If something goes back to normal, it's actually in a robust, benign way, and the pilot has got something to do about it. They didn't have that, so that's the first strike. And the second strike, which is absolutely fundamental in our safety assessment processes in the West. And the second one is this rather unthinking and disorganized management approach, which seemed to exist in Russia. After Chernobyl, the utilities around the world got together, and they didn't just jump on Russia. They said, we all have to learn from this. And they formed a thing called WANO, the World Association of Nuclear Operators, to share experience and to raise the standard of nuclear operators everywhere. And they've had a very positive effect. And it operates in China, it operates in Russia, it operates in the USA, it happens in the UK, everywhere. Well, Bangladesh is just starting up. It'll operate in Bangladesh. This is a human aspect of it. It just copies what happens with pilots, where pilots report problems and they get to the base of it and then share these out with NOTAMs in the aviation world. And the same idea with WANO, to share the best experience and the bad experience, then how to avoid this and push it aside. And I think There was something really important to learn in terms of sharing and best practice and having high standards in operation and the mixing of normal operations with test things and such like. If you have those things together, you have a very safe system. And if you go back to the stats, which most people don't go to the stats, you have independent people who looked at the safety of all sorts of energy generation industries, and nuclear is right at the top. Its accidents have got a lot of attention, which is right, but it's not a poor record. And if you do things right, the record should be zero.
Absolutely. Great additional context. I appreciate going through that. I think it's always great to clear up those misconceptions and kind of give people a realistic idea of, yes, we acknowledge the history, but kind of this current state of where things are today and how safe it is and reliable it is today. A couple more questions as we start to wrap up here. Obviously, this being a renewable energy focused podcast, we always bring different energy parts of that equation into the mix. And there's this argument of sort of nuclear versus renewable energy, which I disagree with. I would love to hear that from your perspective. Like, what should we be thinking about instead?
Yeah, well, we see that over here as well. So one of the things I did a few years ago was, because if you want to make the business case for nuclear, you've got to understand the system it's going to fit into. So you've got to understand the energy system and what the alternatives. And the big new effect was climate change, which means in the future, all energy systems are going to have to either have none or account for or minimize the carbon emissions. In our future system, everywhere we'll have at least 50% renewables. It is the cheapest way to go. It will be the way to go. Some places it'll be much higher than that. Some places it'll be a bit lower than that. But pretty well everywhere, I think I'll have 50%. If you go above 50%, this storage issue becomes more and more acute. But if you actually look at the climate change challenge in most countries, it's not just about electricity. It's about heating. It's about industrial. It's about transport, every damn thing. Unless we use every tool in our box, we will not get the carbon emissions of modern Western societies and the developing countries who want to copy us down. We will need higher temperature sources of energy, which nuclear are good at. You need all types of energy to get to the volume. It's not an either or. It is both.
Yeah, I appreciate you sharing that insight so much. I love having different thoughts and perspectives on the show and kind of covering that. And I've often said it's an and, not an or. We need all of it. And you've kind of brilliantly put that together as well too. And I agree. So I think we've got to get rid of this kind of us versus them type of mentality and coming together and understanding that it's all needed and it will all be necessary, to use all those tools and toolboxes you just shared there. So I love that a lot. I like the perspective. Closing question. If we're thinking about this long term, thinking all things nuclear, by 2035 and really beyond that, what would convince you that nuclear is really just finally really learned how to scale? This has happened. We've gone into this, and it really does take hold and happen at large scale. Like what would convince you? What would need to happen?
There's a lot of enthusiasm and a lot of ideas and a lot of project people working at it, and something good will come out of that. The question is, how will we know when it's good? Yeah. It's all about delivering what it says on the tin. Nuclear does deliver the power, but at what cost and what delay? We have to learn to deliver. If we say the target is to build this reactor in 3 years or 2 years or 5 years, we deliver it in 3 years, whatever it was. If we say it's going to cost X, after the event saying, well, it's unfortunate it was a bit more complicated, we thought it's 3X. You've got to do it X plus or minus 10%. Because if you want people to use a lot of it, it has to be financeable. It has to be attractive. It has to be arrive when the utilities want it. Utilities can't wait. The financiers hate ruining their business case by being late. So doing stuff on the timescales that you say and the cost you say is the sea change we're looking for, which is why I've focused on production engineering. I don't really mind whether it's advanced reactors or light water reactors. They have to meet the mark of providing the power, which nuclear does at the moment. It does it very reliably, but it has to do it not at any cost and not many years late. And it's not about what I promised to do it in 3 years, but it took me 6 years. I promised to do it in 3 years. I did it in 3 years, 1 month. Well, that's okay. We'll let you off the month. But this becomes routine. And this is what happens out of all successful industries. They have to become predictable and regular. And the target by 2035 is to have it to be not a big deal when you order one, because you expect it to come on a particular timescale, and people know how to do it and they build it so it gets done and they move on to do something else. And it becomes unacceptable. It's not lots of explaining why it was exceptional circumstances and why it was very difficult and things. You've got to make it simple. You've got to make it repeatable. You've got to make it on time, budget.
Absolutely. Simple, repeatable, on time, on budget. Great wisdom to live by there. And I guess final thought, like, what gives you hope that it's headed that direction, that this is the path and that will happen?
I think that the number of people are trying. Youth, we get students come to us, but you also talk to these people in these startups. They're very enthusiastic and they have a sense that they're going to do something which is good for humanity. And they have lots of good ideas. They need to go through the safety and testing regime. And some will fail, unfortunately, but some will succeed. I think the idea that it has to be a production process, not a one-off process, to be pretty widespread. These things brought together, enthusiasm, new people, private equity money, and a production engineering approach, I think will get us to a place where it becomes just another industry which is successfully doing what people asked it to do.
Absolutely. Great hopeful points to end on there. And I think great way to wrap up our conversation. Tony, thank you so much for joining us and helping really make such a complex subject much easier to understand. To everyone listening out there, thank you for spending this time with us. If this conversation changed the way you think about nuclear energy, share the episode with someone who would find it valuable. Please subscribe to Green Giants wherever you listen. Leave us a review. It helps more people discover the show and supports the work we're doing. You can also check the show notes for important information about Tony and some links and topics we discussed and additional resources there. Thank you for listening again, and we will see you next time on Green Giants, Titans of Renewable Energy.
This episode of Green Giants, Titans of Renewable Energy was brought to you by Lee Group Search. If you enjoyed today's discussion and are looking to recruit top talent for your company or find your next career opportunity in the renewable energy sector, visit leegroupsearch.com. Let's continue driving the future of clean energy together. Until next time, keep pushing toward a greener future.